Hi everyone, so today we're going to be looking at factors that affect the rate of reaction. And so there's going to be some videos throughout this lesson that you are going to pause and go take a look at. So please do have the PowerPoint lesson also readily available so you can kind of pause and take a look at these videos. So first off is how's the concentration affect the rate of reaction? So when we look at the concentration of a solution, when we look at that, it is measured by the amount of particles, which is our solute, that is going to be dissolved in a quantity of water, and that is going to be our solvent. So if we look at these two solutions, we have solution 1 and solution 2. Solution 1 has more moles per every liter of solution, so therefore it's going to have a higher concentration of particles per liter than in comparison to solution 2. There are some videos posted here, so pause now if you'd like to take a look at the videos, and it can go over these two sections. Okay, so you would have seen in these videos that they're looking at the concentration and how it affects the rate of reaction. So when we look at the concentration on the rate and how it is affected, if the concentration increases, then there's going to be more molecules that are going to be able to react in order to form our products. So because there are more molecules, that is because of that, they are able to collide with enough kinetic energy, enough force, that is our activation energy, to form products. So the more molecules, the more products they're able to form because of that kinetic energy, and therefore the concentration increases the rate of reaction, which also increases. So if we were to look at these two reactions, reaction 2 is going to be faster than reaction 1. That is because there are more particles per liter in reaction 2, as we can see in comparison, those little black dots, and there are more of them. So that means that more products are going to form at a much faster rate than reaction 1 would. So therefore, reaction 2 is going to have more successful collisions. So you can see here, the example on the left is that there are fewer particles. That means there's a lower concentration, which means there's fewer collisions and less products. But the more we have, the higher concentration, the more collisions, the more products. Okay, so we have to look at that based off of how many there are and how the concentration is going to affect the rate. The second thing is that temperature affects the rate of reaction. Okay, so temperature is the second way. There is 2 videos here. For this third video, watch the first 3 or 4 minutes of it and then pause after the 4 minutes, and then the second video there, watch all 4 minutes of it. So pause now, watch these videos, and we can get a better understanding. All right, so you would have seen in the video that temperature does affect the rate. So as we increase the temperature, molecules are going to start moving. We've learned about this in the past in grade 9 and 10. As molecules move faster and faster, there's going to be more kinetic energy because of the molecules increasing. So that means more colliding more frequently, and that means there's more products that are going to be formed because of them colliding, and that increases the rate of reaction because of that higher temperature. And you can see an example here. The lower the temperature, the less the collisions will happen because the molecules are not moving as fast. But if we increase the temperature, then we are able to see more collisions. And once again, you can see here, the increase in temperature causes more particles to move faster because of the kinetic energy. That means the frequency of them colliding is also higher. So as we know, as the temperature increases, the average kinetic energy of the reactants is going to increase, which we learned about before is Maxwell-Boltzmann's distribution shift, and it's going to shift to the right in this situation because of the temperature increasing. So in that region where it shifts to the right, that particle in that area on that graph are the only ones that can collide in the correct orientation. So correct orientation is really important, and if they're not forming in the correct orientation, it's not going to form products. So we have to make sure that their kinetic energy is equal to or greater, okay? This has to be equal to or greater than the amount of energy that is required to break those bonds and then initiate that reaction. So we need to recall that it's really, really important that we have to make sure that it is not only in the correct orientation, but has to have the correct amount of kinetic energy. So if we're looking at the difference between temperature 1 and temperature 2 here, temperature 1 is lower than temperature 2 here. And at higher temperatures, there is a greater fraction of reactants that are going to have enough kinetic energy to create that reaction and start forming. So you can see here, although temperature 1 starts at a higher amount, in our activation energy section, our temperature 2, because it's a higher temperature, is going to have more kinetic energy, and therefore it's going to initiate those reactions. And remember, that curve is really important because we have to have more than the minimum energy that is required to initiate our reaction, and that is what is happening when we have a higher temperature. So if we look at our rates, the rates double for every 10 degrees Celsius that is increase in temperature, and then the rate is halved for every 10 degrees Celsius decrease in temperature. Okay, so temperature is very important for our rate of reaction. I would star this if I were you so you can remember it. If we increase or decrease by 10 degrees, what happens? Next, that affects the rate is surface area. So pause now, watch the video here so you can learn about surface area. All right, so based off of surface area, if we increase the surface area, there's going to be more molecules that are exposed. And then because of that, they're going to have an increase in the number of collisions, and therefore we're going to have more successful collisions that are creating more products that are going to be faster because of that rate of reaction now also increasing. So if we increase surface area, pretty much so far if we increase everything, then the higher the rate of reaction will be. So you can see here, if we increase our surface area, we cut up the boxes into a spread out area, then it will collide more with our products, or our molecules, and it will create more products. You can see here as well, if we break it up, we're not able to get into this inside area. All of this inside area is being missed from the outer layer of atoms, and so therefore if we break it up, there's more chance of collision. Next is the effect of a catalyst on the rate of reaction. So a catalyst does not increase the kinetic energy of a molecule or the number of collisions. So if we have more energy in, it does not mean that there's more energy that's going to be released. Okay? When we look at a catalyst, this is never appearing in a balanced equation. So do recall that we don't have it shown in a balanced equation. But if we are going to show the presence of it, it is written over the arrow, so above the arrow. And if we have a catalyst, it does increase the rate by lowering the activation energy without changing the enthalpy change of reaction. So when we look at a catalyst, it just honestly provides an alternate way. So for example, if you're running through for example, a space, and then you have a catalyst, okay, it allows you to take a shortcut. So if you had a square and you're running around a square, and you were someone who was running, and you're running around the square, if you had a catalyst, it would allow you to cut right through the square because it is giving you an alternate pathway. So in that video 6 that you took a look at, you were able to see, honestly, it's down here if you haven't seen it yet. This video is going to look at how FeCl3 is going to be used as our catalyst that's going to speed up the decomposition of this reaction. So when we look at hydrogen peroxide, and if you buy it in a pharmacy, it's going to eventually decompose. So if you buy hydrogen peroxide in a container, it's actually in like a dark container. The reason for that is because if we have sunlight or increased temperature or whatever it might be, that decomposes and speeds up the reaction. So we want to minimize that as much as possible. And so we want to make sure that the catalyst is not speeding up. So take a look at this video and learn a little bit how it decomposes. Now, if we look at these two graphs here, we have graph 1 and graph 2. Graph 1 is looking at how we have an uncatalyzed energy, so the number of collisions based off of if we have a catalyst or not, and graph 2 is with a catalyst. So you can kind of see here that they're the exact same reaction, but when we have graph 2 with the catalyst, it is going to change our activation energy. Okay, so we are going to have a much earlier and a much larger activation energy, and that's going to cause more collisions going to happen because this whole area is catalyzed energy. This area is not. So therefore, we're going to have more collisions, more products being formed. So I just kind of talked about that here, and so obviously the more molecules that are forming because of that greater kinetic energy, because of that catalyst, then we're going to have more reactions. So once again, a catalyst is an alternate pathway. It doesn't change the energy difference. It doesn't say that there's more energy or less. It just helps speed up the process. Once again, it does not change. Please do remember that because it's really, really important. When we look at the activation energy in a catalyzed reaction, it is lower actually than the uncatalyzed reaction. So you can see here the activation energy only reaches less than halfway of the uncatalyzed reaction. But once again, our pathway is just changing because of that. Okay, our change in age does not change. So when we look at an industrial process here, this does involve a catalyst. So if we were to look at the synthesis of polyethylene, which is our large molecule, you can see here, that is made up of multiple ethenes. When we look at this metal catalyst, it is used to open up the double bond of ethane, and that allows the ethane molecules to join together, and it creates very, very long product. If we look at polyethylene again, once again, it is used in the production of garbage bags, plastic bags, squeeze bottles, so many different examples that is in our everyday life. But when we use a metal catalyst, that is used to make, for example, synthetic rubber, nylon, polyester, Teflon, that catalyst is going to convert your vehicles and it's going to actually create exhaust gas. And it's actually kind of interesting how it is harmless and it's used in our everyday life. So catalysts are literally everywhere. It is used to speed up reactions. It's used in our everyday life, such as in our metal catalyst, polyethylene. We have catalytic converters in our cars. There's so many different ways that it is also used. So these are examples of how we use catalysts in our everyday life. Okay, so we can use it in production of different materials, and that's why it is so important. But we can also use most catalysts in biological ways, which are known as biocatalysts, which help produce living things. So for example, lactase, if anyone is lactose intolerant, that's an enzyme that breaks down the lactase and it is able to digest milk. We also have different enzymes that are produced by bacteria, such as in our yogurt. That is really important, and that is also a catalyst. We also have something called a heterogeneous catalyst, and this exists in a different state of matter than when we look at reactants. It is usually seen as a solid, and when we look at a metal catalyst in a catalytic converter, it is usually in its solid phase while the reactants are seen in a gas phase. So when we look at these heterogeneous catalysts, it's a little bit different. If we look at homogeneous catalyst, it is in the same physical state as the reactant, so it could be a gas or a liquid, which is different than our heterogeneous. So for example, carbonic anhydrase, This is a catalyst that releases CO2 in the bloodstream from our bloodstream into our lungs. So there's different ways. We can either have heterogeneous or homogeneous catalysts, and it just depends on how the reactants and what state that they are in. When we look at our reactants and the nature of them, we can look at pure substances, and when we look at pure substances, we look at its chemical properties. And some chemical properties are only observed when they undergo a chemical change. So, for example, some chemical properties we might look at is how it reacts with an acid. Does it oxidize? What is its reactivity with other elements? So, for example, if we're looking at sodium, potassium, they're going to react really easily with oxygen. So there's different ways that our pure substances are only going to show their properties, and that's based off of a chemical change. We're also going to look at the bond type, the bond strength, and the bond number, and those all determine the activation energy rate that are required for a successful collision. So as I mentioned before, that when we are creating our products, it is important for them to bond and collide, but we have to make sure that they collide at a perfect rate, okay? So bond type, bond strength, and bond number are all very important. When we look at the bond strength and the rates, if we look at weaker bonds, they're going to be broken faster than stronger bonds, and so therefore it takes less energy to break, for example, a single bond of carbon than a double bond of carbon. If we look at the number of bonds, if we look at the reactions involving smaller bonds per reactant, they proceed faster than those involving the breaking of larger bonds per reactant. And then if we look at the type, if we're looking at the reactions between molecules, they're going to be usually slower than between ions because those covalent bonds must be broken and new bonds have to be reformed. So these three types are really important when we're looking at the successful collision of activation rate. So for example, if we're looking at these two examples here, reaction 1, reaction 2, reaction 1 is ionic, reaction 2 is covalent. And so therefore, if we look at reaction 1, it's going to be faster because it's ionic and it's a metal and non-metal. Meanwhile, our reaction 2 is not going to be as fast. It's not as easy for it to break the covalent bonds. And so therefore, because reaction 1 has the separate into compounds, it is faster. Also on top of that, the shape and size of molecules or ions does affect the rate of reaction. So if we have a very large molecule or a more complex molecule, it's going to have a slower rate of reaction. That's because we have more bonds to break and it's less likely to collide in the correct orientation. Once again, the correct orientation is very important. As I just mentioned, that is based off of the bond type, okay, the bond strength, and the bond number. This is all a part of that. So if we're looking at these two examples here, we can see that one is going to be faster than the other. We have our C3H8 is much smaller molecule and therefore has fewer molecules to break. So because it requires less energy to break it, therefore it will be faster. Okay, so the larger it is, the more complex it will be and the slower it will be. So this reaction here will be slower. So we have some textbook questions. If you have any questions regarding them, let me know. The answers to these questions above are going to be posted after these slides. So let me know if you have any questions. Other than that, I'll talk to you later.